So good morning, student. Today I will be teaching you hydrocarbons. So what are hydrocarbons? So hydrocarbons are the compounds of carbon and hydrogen. Hydrocarbons are the compounds of carbon and hydrogen. Now classification of hydrocarbon, types of hydrocarbons. There are basically three types of hydrocarbons: saturated hydrocarbons, unsaturated hydrocarbons, and aromatic hydrocarbons. In under saturated hydrocarbons, we have alkanes. So in saturated hydrocarbons, you have only carbon-carbon single bond. In unsaturated hydrocarbons, you have carbon-carbon double bond as well as carbon-carbon triple bond. If double bond is there, they belong to alkenes. If triple bonds are present, then it belongs to alkynes. Aromatic hydrocarbons, they are derived from benzene. Benzene is the parent aromatic compound and its derivative. For a small trick I want to give you to identify aromatic compound is CpCH. What is the CpCH? Cyclic. The aromatic compound must be cyclic. It must be planar, means sp2 hybridized. It must be conjugated. Conjugated means having alternate double bond, single bond, double bond, single bond, and it must obey Huckel's rule of 4n plus 2 pi electron. Huckel's rule of 4n plus 2 pi electron. Now coming to hydrocarbons, they are broadly classified into acyclic or open chain or aliphatic, or cyclic or closed chain. Under acyclic or open chain or aliphatic, there are saturated as well as unsaturated hydrocarbons. The saturated alkanes are also known as saturated hydrocarbons. They are also called paraffins. They are also called paraffins because they have little affinity to react with acid, base, oxidizing agent. Under unsaturated hydrocarbons, alkenes and alkynes are there. Alkenes are also called olefins because the lower member forms oily product with chlorine. Alkynes are also called acetylene because the first member is acetylene, which is used in oxyacetylene torch for welding metals. Under cyclic or closed chain, there are alicyclic and aromatic. Under alicyclic, there are saturated and unsaturated. Under saturated, there are cycloalkanes. Under unsaturated, there are cycloalkenes and cycloalkynes. Under aromatic compound, if they have benzene ring, then it is called benzenoid aromatic compound. If they don't have a benzene ring, they are called non-benzenoid aromatic compounds. Now today's discussion will be we will focus more on alkanes. So the general formula of alkane is CnH2n plus 2. It is also represented by RH, where R is an alkyl group. R is an alkyl group. Alkanes have only single bond, carbon-carbon single bond. There is no pi bond, so pi bond is 0 in alkanes. They are regarded as saturated hydrocarbons. The hybridization of carbon in alkane is sp3. The bond, the HCH bond angle is 109°28', and they are tetrahedral. Only sigma bonds are present in their structure. They are very less reactive, and that's why they are also called paraffins. They have less affinity to react with acid, base, because the carbon hydrogen bond is almost regarded as non-polar. There is no polarity because the electronegativity of carbon is 2.5, whereas the electronegativity of hydrogen is 2.1. So there is very slight difference in electronegativity. So this bond is almost treated as non-polar. Its bond is almost treated as non-polar. Now, if you see the excited state carbon configuration, it is 1s2, 2s1, 2px1, 2py1, 2pz1. So what happens? One of the s electron goes to p. So this explains the tetravalency. So this 4 orbital mixes each other to form 4 sp3 hybridized orbital, which is directed at the corners of a regular tetrahedron with 4 hydrogen, combining it to form methane. So in methane, the bond angle is HCH bond angle is 109°28'. The shape of methane molecule is tetrahedral. Keep in mind that in alkene, the carbon hydrogen bond length is 1.09 angstrom, and the nomenclature of alkane. So you have to write the word root plus n. N is the suffix in alkane. Like for 1 carbon, it is meth. For 2 carbon, it is eth. For 3 carbon prop. For 4 carbon but. For 5 carbon pent. For 6 carbon hex. For 7 carbon hept. For 8 carbon oct. For 9 carbon non. For 10 carbon dec. For 11 carbon undec. For 12 carbon dudec. Like that, you have to start. Now, if you have a bond line structure like 1, 2, 3, 4, so this is simply normal butane or butane. If you have a branching, this one stick is methyl, so it will be 2-methyl propane. It's 2-methyl propane. Now, if you have 2 branching, then you can just find the longest carbon chain, and based on that, you will find that it is 2,3-dimethyl butane. It is 2,3-dimethyl butane. If you have this caustic sign, then it is 3,3-diethyl pentane. If you have this cross sign, then it is 2,2-dimethyl propane. The common name is neopentane. Now coming to isomerism alkane, so mostly chain isomerism and conformational isomerism, which will be discussed in detail. Now coming to methods of preparation. So first method is by hydrogenation. Hydrogenation means addition of hydrogen. So when you add hydrogen to an unsaturated alkane, to an unsaturated alkene and alkyne, you get a saturated hydrocarbon like alkane. So let's see. So if you have ethene, and you are treating with hydrogen in presence of nickel catalyst, you get ethane. So ethene on hydrogenation in presence of nickel will give you ethane. This reaction is called Sabatier-Sandrens reaction. This reaction is called Sabatier-Sandrens reaction. With nickel, it must be heated. Without nickel, like with palladium and platinum, the reaction occurs at room temperature. The reaction occurs at, so ethene reacts with hydrogen in presence of palladium or platinum to form ethane. So you can remember the trick, Nikah Padhe Pandit. Nikah Padhe Pandit, this is the catalytic hydrogenation catalyst. So remember this. With nickel, it must be heated at 200 to 250 degrees, but with palladium and platinum, the reaction occurs at room temperature. With nickel, the reaction is also called Sabatier-Sandrens reaction. With nickel, the reaction is also called Sabatier-Sandrens reaction. Now, if you take ethyne, then you have to take 2 moles of hydrogen, because ethyne first will be converted to ethene, and then that will further react with hydrogen in presence of the catalyst to form ethane. But here the more better catalyst is Raney nickel. More better catalyst is Raney nickel. You can watch a video in my channel about Raney nickel. Next method of preparation is from alkyl halide. So if you have alkyl halide, if you treat it with a reducing agent, it becomes alkane. It becomes alkane. So I will be giving you a host of reducing agent which will be quite useful to you. So list of reducing agent which is used to convert alkyl halide or haloalkane to alkane. Zinc plus NaOH first. Next, zinc plus acetic acid. Second. Third, sodium in ethanol. Third. Fourth, lithium aluminum hydride. Keep in mind that lithium aluminum hydride only reduces 1 degree and 2 degree alkyl halide. It gives alkene with 3 degree alkyl halide. So 3 degree alkyl halide will not reduce to alkane in presence of lithium aluminum hydride. Very good reducing agent, also written as La. Now coming to palladized charcoal hydrogen, zinc copper couple, these are all reducing agent which will reduce alkyl halide to alkane. Sodium borohydride, but it will reduce only 2 degree, 3 degree. It is unable to reduce 1 degree alkyl halide to alkane. Magnesium amalgam water, this is also acting as a reducing agent. Another is TPH, it's a very good reducing agent. It is called triphenyltene hydride. It reduces all 3 different classes of alkyl halide, that is 1 degree, 2 degree, 3 degree. Another reagent which is useful to reduce the alkyl halide is tertiary butylene hydride. It is very selective reducing agent because it can reduce only alkyl halide as well as nitroalkanes. So only these and other functional groups are unaffected by tertiary butylene hydride. So these are the host of all different types of reducing agent used to convert alkyl halide to alkane. Now coming from alcohols, so if you treat alcohols with phosphorus and iodine, then it will form alkane. So keep in mind that first it will form alkyl halide, then it will be reduced to alkane. Next is tosyl chloride. What is tosyl chloride? So 4-toluene sulfonyl chloride is also called tosyl chloride. So when an alcohol reacts with tosyl chloride, it forms the alkoxide derivative of tosyl chloride, which when treated with lithium aluminum hydride, a reducing agent, will give you alkane. Now keep in mind that tosylate ion is a better reducing group. This you will read in SN1, SN2. So it's a very good leaving group, best leaving group. Now, next method is from carbonyl compound. So reduction of carbonyl compound will give you alkane. This can be done by different methods. So first, red phosphorus and HI, a very good reducing agent, very good reducing agent. It will convert. So here you are seeing the carbon oxygen double bond. This will be converted to CH2. So carbonyl compound ketone can be easily converted to alkane. If you take a specific reagent like zinc amalgam HCl or conc HCl, you will get alkane, and this reaction is called Clemenson reduction. This you will also read in aldehydes ketone chapter. So when ketone or aldehydes is treated with zinc amalgam HCl, then it will give alkane, and there is no change in the number of carbon. Here also it has 3, so here also a product with. So there is no ascent or descent of series. Now, if you treat a ketone with hydrazine and then treat it with alcoholic KOH in presence of a glycol, then you will get alkane. This reaction is called Wolff-Kissner reduction. This reaction is called Wolff-Kissner. Recently, IIT also asked question based on Wolff-Kissner, so keep this in mind. Next is from carboxylic acid. From carboxylic acid. If you take carboxylic acid and treat it with red phosphorus HI, you will get alkane. So acetic acid will give you ethane. Acetic acid will give you ethane. If you have benzoic acid, then you will get toluene. So what happens? The COOH group will be converted to an alkyl group. Next reaction is from metal carbides. This has been asked in IIT, so keep this in mind, student. Aluminum carbide when treated with water will give you methane. Similarly, beryllium carbide when treated with water will give you methane. So very, very important reaction. Aluminum carbide and beryllium carbide on treatment with water will give methane gas. Will give methane gas, one of the simplest organic compounds. Next is Berthelot synthesis. Next is Berthelot synthesis. Here carbon is treated with hydrogen in an electric arc in presence of electric acetate. It gives methane. If you take more number of carbon, means excess carbon and hydrogen will give you ethane. So this is Berthelot synthesis. So Berthelot was the first to synthesize methane. Woods reaction. When 2 moles of alkyl halide is treated with sodium in presence of dry ether, we get alkane. We get alkane plus sodium halide. So this method is more useful for the synthesis of symmetrical alkanes. This method is most useful for the synthesis of symmetrical alkanes. If you take 2 different alkyl halide, then what happened? A mixture of alkanes are formed. Like in this question, which IIT asked. You have methyl chloride, you have ethyl chloride, and you are treating with sodium in presence of dry ether. So what will happen? It will form ethane, propane, and butane. Suppose methyl chloride only reacts with sodium, then it will form ethane. If suppose 1 molecule of methyl chloride and 1 molecule of ethyl chloride react, then it forms propane. If ethyl chloride only reacts with sodium, then it forms butane. So mixture of products are formed which are difficult to separate. So this question was asked in IIT. So next is decarboxylation. So if you have salt of carboxylic acid like sodium carboxylate, you treat it with soda lime. So mixture of NaOH plus CaO is called soda lime. It's called soda lime. So this will give you alkane. So sodium ethanoate will give you methane. So this reaction is an example of descent of series because the number of carbon formed in the product is less than the number of carbon present in the reactant. So thank you for watching, student.